My name is Ross Mitchell, and this is just cover in the bio, really. I'll just go over it quickly. So I started got my PhD training at the University of Western Ontario, and I was a prof there until 2000 when I moved to Calgary to set up a lab at Foothills Medical Center in radiology. And I was there for 11 years until I got recruited by Mayo Clinic to go and set up a division of medical imaging informatics for them at their Phoenix campus in Arizona. And I was there for 8 years. And then I got recruited by Moffitt Cancer Center in Tampa, Florida. A lot of people may not have heard of Moffitt. It's the third largest cancer center in the US by patient volume. And it's the only National Cancer Institute designated comprehensive cancer center in the state of Florida. Florida has about 24 million people live in Florida. And so that's why they tend to be old. So that's why Moffitt has such a large patient volume. So I was their inaugural AI officer, and I did that until the end of last year, when I came back to Edmonton to start the role here as the chair in AI and precision health and to help Alberta Health Services with their AI plans. So the focus of my career has always been on the clinical side, so the development and translation of tools, not just development and publication, but to try and actually get them across the vast divide or the barrier, the fence that splits academic research in AI from medical application of AI. So these are some projects that I worked on over the last couple of years. Worked on analyzing data in electronic health record, doing some natural language processing, and I've always done imaging throughout my career. My PhD was in medical biophysics, and it was medical imaging physics, actually, although I was more on the post-processing side. So I've got a couple of decades of experience in medical imaging, and the other stuff has come more recently, the NLP and the EHR analytics. So today I'm just going to talk about 4 things. That's it, 4 things. EHR analytics, about sepsis. We've already seen a lot of talk about sepsis, predicting lung cancer mortality, NLP, and some imaging stuff. So the first thing, when I got to Moffitt, they were quite interested in having me develop an algorithm to predict sepsis in bone marrow transplant patients. And I'll let this play, but most of us are, especially after giving the talks this afternoon, we're familiar with sepsis. It starts quite often with an infection somewhere in the body and causes an immune reaction that gets out of control, and you go into septic shock. At Moffitt, they had employed several sepsis sniffers, as these algorithms are called. Their electronic health record system is made by Cerner. Epic has one as well. And there are some commercial ones that you can buy. So they tried all of these and none of them worked. And that by not working, it means, in their case, way too many false positives in these bone marrow transplant patients. And at Moffitt, they define somebody as being septic if they meet 2 or more of the SIRS criteria. I've listed them there. I'm not going to go into them too much. Sepsis is kind of vaguely defined. There are multiple criteria and multiple ways of defining whether you have it or not. And what's tricky about it is physicians often know when it's there. After it's active and flamed up and running and the patient's in trouble, they recognize that it's sepsis, but 4 hours before that, they don't know that it's sepsis. So it's really hard to diagnose until it's fully raging. And in bone marrow transplant patients, you can imagine you have on purpose reduced their immune capacity. Obviously, you've removed all their bone marrow ahead of the transplant. So these folks are at very high susceptibility of getting infections and therefore sepsis. So the target group is inpatients. So patients come in about a week before their scheduled bone marrow transplant, and they undergo a bunch of tests. And one of the things they do is they have their existing bone marrow completely obliterated. And so they're the equivalent of an ICU essentially, but it's the pre-bone marrow transplant ward. Moffitt does about 300 patients a year, bone marrow transplant. And so we looked at about over 10 years worth of data. It was about just under 6,000 bone marrow transplants that we looked at. And we had about just over 500 positive cases. So that's a positivity rate of about 10%. And you see that a lot in medical data sets. They're highly unbalanced. It's rare that you get the positive and negative classes being equal. 10% positive is pretty common. Sometimes it's even less than that. So we used ICD codes to identify sepsis, severe sepsis, or septic shock. Any of those codes were enough for us to include the patient. And we were asked to screen just for those patients who had sepsis post-onset their bone marrow transplant. And that's where the 5,500 and 5,800 and 561 numbers come from. So the goal was to predict post bone marrow transplant sepsis 5 days ahead of time. And you might ask, why 5 days? Because that's the measurement, the data measurement frequency. Once they've had the bone marrow transplant and they're in the equivalent of an ICU, they're hooked up and they're monitored and you get a lot of treatment. Then they spend about a week to 10 days in that unit, and then they're released to ambulatory care, and they spend the next 6 weeks in the vicinity of the cancer clinic, and they have an in-house appointment every second day to monitor how they're doing. And in that ambulatory setting, we don't get much data off of them. So used a standard machine learning algorithm. It's one of my favorites. It's a go-to, XGBoost, based on it's a random forest essentially on steroids, with a 60-day trailing sliding window. So we looked at all the data from that patient over the previous 60 days and tried to use that to predict. So after we did a bunch of cleaning and normalization, we ended up with about 500 variables covering a range of things, so including the labs, drugs, biomicro results, the disease, patient demographics, all that sort of thing. And our model looks like this: area under the curve of 80%, positive predictive value just under 70, and a negative predictive value of just under 90. It sounds good, but it's not good enough. This model was deemed to be insufficient quality to be put into clinical practice. But it was worthwhile for us to build it. We learned a lot about building it. And we actually decided to go ahead and begin the process of running it in shadow mode. So when you, in the clinic, when you build a model, you don't build it today and start using it on the ward tomorrow. Typically what you do is you run it in this data collection mode for, depends, you have to figure out your numbers. In our case, we were going to run it for a year, and we would collect data every day from all the patients that were on the ward getting queued up for their bone marrow transplants or had just had them. And then once a month, we were planning to sit down with the infectious disease docs and the quality people and look at the data retrospectively to see how the model is doing. And this helps you tune your model over that year period. The model doesn't have to be implemented in the electronic medical record because it's not being used for clinical decision-making. It's just there for retrospective analysis. And it also helps you build trust with the clinical team. They get to feel what the model does and where it makes mistakes. Guaranteed you're going to be making lots of mistakes with these early models. So basically, you're running like a randomized controlled trial of this new intervention. So, but we were doing this more just to learn. They had determined that a positive predictive value of 70% wasn't good enough. We're still going to get too many false positives out of that. And remember, 1 in 10 of our patients, only 1 in 10 of these BMT patients get sepsis anyway. So if you just said nobody gets sepsis, you'd be 90% accurate, right? So we're at 84% overall accuracy. We've traded off some of the negative predictive value to increase our positive predictive value dramatically above the default sort of 10%. Anyways, we went back to building a tool which is to analyze EHRs in general. It's something we've been working on for the last couple of years and something that will apply here in Alberta. And we made an interesting discovery. So I asked the fellow who's working on this with me to just produce a plot of all of our students, all of our patients. And this is a plot of the days between when their bone marrow transplant happened, which we call day 0, and when we picked them out of the electronic health record with an ICD code that indicated they had one of those conditions, septic shock, and so on. And we got this distribution. And I've colored them here into red and blue. So by definition, we were asked to include only those patients who got sepsis after their BMT, which means above day 0. So our model included all the patients that you see in red there, and the height is the number of patients, of course. And I looked at that and said, what the heck is going on with all those patients in blue? Look at the massive spike. Are you telling me, so all of these patients got a bone marrow transplant. That was one of the selection criteria. And these are the ones that got sepsis in addition to getting a bone marrow transplant based on their ICD codes. So I looked at this and said, are you telling me that somebody went fully septic 5 days before their bone marrow transplant and they still did the bone marrow transplant? No way. absolutely no way. There's something wrong here. Like there's something going on here. We have to figure out what's going on. So we started to dig into it and we discovered something really interesting. When the infectious disease doc is on the ward, they write up their notes, and they used to also do coding. They used to enter some ICD codes, but they took that away from them and they put that over to the billing department. And in the billing department, they go and look through the notes from the doc and they look for catchphrases and they assign codes to that. But what they do when they're assigning a date to the code is they assign the date that the patient was admitted to the ward, okay? Not the date that the code was actually physiologically relevant, okay? So if, suppose they were admitted to the pre-op ward on Monday and their BMT is on Saturday, and then the next Monday they develop sepsis. They're technically in the same ward, so the date is assigned to the first Monday by the billing department. Does that make sense? So I couldn't believe that the billing department was putting codes down that weren't tied to the physiology of the patient, but this is standard practice. We didn't know as machine learning guys. We figured that if you put down an ICD code that says the patient went septic, they went septic that day, or, you know, more or less, not 10 days before, right? So they were saying they got admitted to this ward and 15 days later they went septic, but the date of the code is day 0, not day 15. So really, we were picking the wrong patient population. We should have been analyzing all those patients in blue and very few of the patients in red. And this is happens all the time when you're building models. You got to look at your data. You got to get right down and dig into it. And I don't know how many times I have to learn this. I keep making these mistakes all throughout my career. You need to look at your data first before you start building the model. And we had talked to we were integrated in with the ID docs and with the quality team, and we were part of their rounds, and they didn't know about this either. They didn't know that the billing department was doing this. So when this is all said and done, we went back and said, well, the billing department has to change how they do their coding. And the response was no. Why would we do that? We've been doing it this way for 10 years. Why would we change? And you get that pushback too. So it really takes like somebody at the top to convince the people on the administrative side of the organization that they need retraining, they need to update their records and go back. And it's a lot of expense and trouble to get the billing folks to change what they do. But if you don't do that, garbage in, garbage out. So part of this, we built a tool. They said, well, let's actually look at the data. So we built this tool. And what this is showing a plot for a specific individual patient. And this is all running in a web browser. And you can type in the MRN, the medical record number, the unique identifier for that patient. And when you type it in and hit return, this plot is produced immediately. And it shows all the measurements across a broad range of data for that patient going back as far as you want. But it typically starts with about the last 60 or 90 days. You can zoom in, you can scroll, and you can hover above any of those data points, and it tells you the actual values that are in the EHR. And we use this just to get a feel for our data. And the bands there, if it's green, it's in the acceptable range. And if it's red, it means that it's outside the range and would be one of the positive criteria for sepsis. Remember, we needed 2 or more of those to call them septic. So we built this for ourselves and we were playing with it. And I thought, I wonder if this would be useful to the folks on the ward, like the nurses or the quality team. So at one of the rounds, we showed this and their jaws just hit the floor. And they said, we have people on our team whose job it is to do this, some of this, but they have to go through Cerner page by page and write into a spreadsheet the value of arterial pressure. And they might look at something else and they'll go back 2 weeks and extremely labor intensive. And they only do it for patients that they really realize they missed something on. And so when they saw this, they couldn't believe it. So we deployed this and now they can go up to the ward with their iPad, type in an MRN number, and this just pops up immediately. And they can compare, so they can flag some and say, this patient's interesting. And then when they come back, they can compare to that one that they saved. So they have a favorites list. And it turns out that this is probably more valuable to them than our sepsis prediction model, right? We were planning to put our model, superimpose it on this so you could see patterns and what variables it was using. And if you look at this sort of thing for a while, you can, I can see things by looking at it. I can see they probably missed a couple opportunities to pick up that this patient might go septic. I don't know if you can see at the very right of this, when the respiratory rate goes way into the red bands, that's when this patient actually is septic. But there's a couple similar patterns before that. And as a human, you get good at seeing patterns and things. So this may help them more than any fancy model that we ever come up with. But we didn't, because they shut us down on this project. And I said, oh, we trained on the wrong data. They said, so sad, too bad, on to the next project. And that happens a lot in clinical medicine as well. You just don't have time to get back to it. So the next thing I want to talk about is a variant of this. And it was to predict lung cancer mortality. So a friend of mine who's an oncologist deals with these patients, and he said they're very interested in trying to predict whether these lung cancer patients are going to live 120 days or not. And I said, why? And there's a bunch of reasons why. In the US, you get penalized if you treat patients within 30 days of being admitted to hospice. And within 90 days of them passing away, you actually get financially penalized if you do that. So there's that aspect of it, but they also want to use it to help routing and help plan for family planning and end-of-life care, end-of-life planning. And so, you know, these are numbers from publications. It's pretty interesting. 13% of adults get chemotherapy within 2 weeks of them passing away. That probably shouldn't happen. Over 20% get radiotherapy within 30 days of death. That probably shouldn't happen. It's not helping them. It's costly. It may even make them feel worse at the end of their life. So the focus of this particular group was these patients are very frail. They're quite weak, so they're not candidates for surgical intervention to remove their lung tumor. So instead, they use a very intense focused beam of high intensity radiotherapy to essentially burn the tumor out. And it's almost like surgery without cutting. You're just blasting this nodule in the lung, and it's not curative, but it's meant to be palliative. But they're frail with poor overall survival. And my friend, the doc, said he has no idea. He mentally, he makes a note and tries to guess who he thinks is going to be alive and, you know, live 3 months or not. And he says, I'm as good as flipping a coin. I have no idea. He says, sometimes a robust person comes in and they're gone in 2 weeks, and a frail old lady comes in and she's alive 2 years later. He says, I'm just terrible at this, but if you could build a model, that would be great. So again, we have about a 10% positive vote, 3,000 total records, 734 unique patients. We looked at just about 1,100 particular records of these patients who, and just over 100 of those went on to pass away within 120 days. So again, a 10% positive rate. So 90% of our patients survived beyond 120 days, and 10% of them did not. And what was cool about this is he had a nice database, and from presentation of the problem to this model was 7 days. That's all it took us to build this model. And that's because we had this toolkit built, and we had used, it's basically part of the same toolkit that we used for the sepsis problem. We just reapplied it. And this is a cross-validation. So we always like to do a cross-validation first to see if we're even in the ballpark, and then you go on and do a proper sequestered test data set. But for the first pass, we like to do this. And here our positive and negative predictive values are pretty decent. It's not bad. So we're able to predict pretty well. The next question is, how does it work? You got to give some explainability to the clinician if they're going to trust this. So one of the things we like to do is something like this. It's called SHAP analysis, and it's basically like doing multiple logistic regressions. Sorry. And it shows you the effect of various variables in your model and how they contribute to the model's final decision. So the SHAP value, those colored blobs, if they are on the left of that center line, that tends to decrease patient mortality. And if they're on the right of that center line, it tends to increase patient mortality. So look at the top row there, it says age. And the color of the blob tells you how it falls in the range. So blue values are at the low end of the range, and red values are at the high end of the range. So in age, a blue dot means you're young and a red dot means you're old. Does that make sense? So clearly it's saying that the younger you are, the higher your chances of surviving are. So you do better if you're younger is what that says. That makes sense. We would expect that to fall out. But there's a bunch of really cool stuff in here. And one of the first things I noted is all these things that are tagged ESAS. How many people here have heard of ESAS? You guys hear about this in your, it stands for the Edmonton Symptomatic Assessment Score. And they use this extensively in these big cancer centers in the US, and Moffitt's all over this. See, when you come and sit in the waiting room, they give you an iPad and you fill this out. Every time you come, you fill this out. And there's 10 variables that are measured, and it's how you feel. Are you sleeping well? Do you feel comfortable? Or, you know, how's your digestion? Things like that. Overall well-being is one of them. And a low score means excellent, 0 means excellent, and 10 means really bad. So it's semi-quantitative and it's quite subjective. But look, it ends up being almost all of those variables end up in our final model from the 500 plus that we started with. And I thought, this is really cool. So I asked the guy who's working on this, the scientist, I said, let's just build another model with just the ESAS and the fixed patient attributes. And this is the resulting model, and it's just as good as the previous model. We didn't lose anything by just focusing on the patient reported outcomes, and there are things like gender and age and weight and stuff like that. And that tells you a lot. It tells you that we don't need all the lab values to predict mortality. We don't need all the biomicro test results. We don't need to know what drugs they're on. We just, if they tell us how they're feeling, that will allow us to predict pretty well whether they're going to be alive in 120 days or not. But one of the other things that's cool about a model like this is things pop out that you might not expect. So I always say never pre-select your variables if you don't have to, because that brings a bias. It brings the clinician's view or the data scientist's view of what we think should be in the model. And that we lose an opportunity to find interesting patterns. So here's one: radiotherapy year is one of the big predictors of how patients are going to do. That ranges from a low of 2015 in blue to a high of 2019 in red. So if you were treated in 2019, you did way better than if you weren't. Why? We don't know. Maybe they changed the way they code something. Maybe they got a new piece of a new LINAC in the radiotherapy department that had more accurate treatment. We don't know why. Here's another one. This might be more expected. If you lived in a highly rural to urban is graded on a 10-point scale, 1 being highly urban, like living here near the university, and 9 being very rural, out in the boonies in the middle of Florida. And if you lived in a city center, you did better than if you lived out in the country. Well, okay, maybe it takes more time and the people out in the country don't come for all their appointments and everything. We don't know, but there's probably something going on there. And then, of course, these ESAS variables still come through. Pain, constipation, and lack of appetite are real good predictors of whether someone's going to be alive or not. Their income is a factor. The type of tumor they have, where it is in the lung, these are all things that are interesting that pop out. And this gives you ideas to go back and do additional experiments to try and figure out what's going on. Okay, the third thing I'm going to talk about is some natural language processing work that I did. And you can see there's a whole presentation I did on this for NVIDIA at their big AI conference that they hold once a year. It's coming up in about a week, but so a year ago, almost exactly, I gave this to them. And it's online. You can just Google NVIDIA 2021 NLP and pathology and take you right to my talk. So this is something they asked me to work on when I arrived at Moffitt in early January of 2019. They said, we have this real problem with pathology reports. They're very terse, but they're loaded with information. So this is a real sample segment of a pathology report from Moffitt. This is exactly what they look like. And if you read through this, you can see there are a bunch of negative indications here, negative for malignancy, and so on. But down at the bottom, it says large cell carcinoma undifferentiated. And it also says lung right lower lobe. So this is a positive indication. This patient got a bunch of tissue samples. Most of them were clear. There was no cancer, but at least one of them was. And the cancer is a large cell carcinoma, and it's in the lung. Wouldn't it be great if we could have a way to extract this automatically? Because what happens now is this is read by somebody called a certified tumor registrar. And tumor registries exist in pretty much every cancer clinic in the Western world. And what these folks, it's about a 2-year post-high school training and a 1-year internship, and then you get certified to read pathology reports and extract things like site and histology and stage and those sorts of things from the pathology report. And that gets entered into a database, and it's used for planning and reporting, and it's also useful for research studies. The problem is most cancer clinics are about 12 to 18 months behind. So you get the PATH report today, it'll be 12 to 18 months before that shows up as a searchable field in a database. So if you want to enroll someone in a clinical trial, you got to hire someone with expertise to go through entry by entry and manually read the pathology report and find out if they're eligible for the trial. So it can really slow down enrollment in clinical trials. So people have tried to tackle this for many years. It's a huge problem, but the techniques that they've used have been okay, but the accuracy isn't great. But just before I arrived at Moffitt, Google published BERT. How many people have heard of BERT? Oh, awesome. Lots of people have heard of BERT. So it's a big natural language model, and it just has revolutionized this whole field of transformers, of which BERT was the first major one. Has revolutionized natural language processing. Over 32,000 citations in just over 2 years, 3 years. It's pretty impressive. But it hadn't been applied to pathology reports when I started on this. And a part of the issue is that these pathology reports, they're not regular English prose. If you train on Wikipedia or the works of Shakespeare, it's not going to help you much interpreting these pathology reports. So if you take an open source model that's been trained on that kind of data and download it and apply it to these pathology reports, you wouldn't expect to get great results. So the first thing I wanted to do was to train a model on the language of pathology. And this is unsupervised. So you just crank through a bunch of data. And I can describe in detail how that's done, but the important thing for you is you just give it data. It churns on it, in my case, for about a week on a powerful computer, and it starts to learn about the syntax, organization, structure, and some of the special terms that are in that language. So I built a system that used a question and answer system because BERT has been particularly good at this task of language understanding, answering questions. And so I thought, well, let's just hard code some questions and see how it does at answering it. So I hard coded 2 questions: what organ contains the tumor and what is the type of tumor? And then I said, go and find the answer for this in these pathology reports. And we got our truth from the cancer registry, because they've already extracted this. So I went back and trained this on about just under 300,000 digital pathology reports from Moffitt. And one of the cool things was, because I was on the clinical side of the house, and this is a clinical improvement project, I didn't have to go through IRB approval. It's clinical improvement. And so I said, I need some pathology reports to train my model. And the database person I was working with said, well, how many do you need? And I said, all of them. Give me all of them. She said, okay. And about 7 days later, I had 500,000 digital pathology reports. There was a lot of duplicates in there, which we found out later. So the real number of pathology reports unique is about just under 300,000, 275,000 or so. And then we have a bunch of filtering to make sure, double check, double blind, to make sure that the diagnosis that the cancer registry came up with was actually confirmed by somebody else independently. So you have really good ground truth data to train the model. So we ended up with about 10,000 of these really high quality the reports or whatever they are, but the high quality ground truth. We're pretty confident in the labeling. So we set just over 8,000 of them for training and totally sequestered just over 2,000 for testing. And this represented 193 different histologies across 214 sites in the human body. And you might expect that at a large National Cancer Institute cancer center that is the 3rd largest in the US. They're going to have just a vast array of patients coming in with all kinds of rare cancers, and the common ones, of course, as well. So what did we do? Well, we built a new language model that's specific to pathology. We call it CancerBERT. It understands the language in pathology reports. This is something I would like to open source. We built a new question and answer system to find the answers to these 2 questions, but it's extensible. You can add more questions, and as long as you got the truth, you can train it very quickly and extend the system to find other things. And I'll show an example of that. And then we built a new network to not just extract the phrase that corresponds to the organ and the histology, but to map that onto standardized terminology. And we used ICD-0, which is the International Classification of Diseases for Oncology. And it's commonly referred to as the purple book. So all the cancer registrars walk around with this thing under their arm, and it's about 1.5 to 2 inches thick. And their copies are just littered with sticky notes sticking out for their particular, like they're subspecialized on lung and they subspecialize on gut or whatever. But all the their books are tagged so they can get to that page very quickly. So when they're sitting there reading the report, they go, no, is it this or this? They'll go to the purple book, bring it up, flip it open and check and see what the rules are. And inside this book is a list of all possible cancers that you can get and a list of all possible organs that they can affect. And for each organ, the cancers are listed out. So we use that. And after we built the network, we did some testing, and this is basically what it looks like. You have your pathology reports, the 2000 sequestered pathology reports. So we pull a pathology report out and we'd feed it into CancerBERT, which is the language model. It understands the language of pathology reports. And then I trained, you can think of it as a snap-on head. It was something that takes the output of CancerBERT and then uses that to try and find, it does the question and answering. It says, it tries to answer the question, where's the tumor and what is the tumor, and produces that as output. So it might produce output that's something like this, literally site, colon, upper lobe lung, HIST, shorthand for histology, adenocarcinoma, NOS. And once we have that, what we do is we take that phrase and feed it into two downstream networks. They use the same base language model, but now I train two different Snap-on tool heads, one to predict the site code and one to predict the histology code from the purple book. And you might wonder, well, why do you pass the site information to the histology classifier and why do you pacify the histology info to the site classifier? Because, and the short answer is they're correlated. Some types of tumors only occur in certain sites, or they're more probable in certain sites. So it can leverage that information to improve its performance. For example, if you have a glioblastoma, it's a type of brain tumor, only happens in the brain. You're not going to get that in your liver. So the pathologist will often just say the histology is glioblastoma and never mention that it's in the brain. That's nowhere in the pathology report. But our system learned to see if it was glioblastoma, it would always fill in brain as the organ, even if that wasn't in the pathology report. So the output from those are these codes, and they look like this. These are essentially really smart lookup tables. And then when we've got those codes, we can compare them back to the ground truth from the cancer registry to see how we did. And so this thing, the whole thing together, this whole pipeline is called the CancerBERT network, and we just call it Cabernet in practice. So how'd we do? So these are fine-grained codes, as fine as you can get, according to the ICD, the purple book. And this is a plot of our results. And I'm showing site, and there's two colors here. I'll get to those in a minute. But this top N is basically a description of how often the correct answer is in the top 5, let's say. That's what 5 represents. The green line represents if we cull really, really rare cancers, cancers with less than 5 samples in all the training data. So in the last decade, they saw 5 or fewer of these patients. Not quite at Moffitt. They might have seen more than 5, but we couldn't be convinced, sure of their diagnosis. We couldn't verify it independently. So in our 10,000 or 8,200 cases that we used to train, there were fewer than 5 of these. So it's a pretty rare cancer if a big cancer center is only seeing a few of them over a decade. And the hypothesis was there's just not enough there to learn off of. We don't have enough training samples to learn. But we also looked at when we did no culling whatsoever, and that's the blue line. So in this case, the correct answer was in the top 5 answers just over 91% of the time without culling the rare cancers. And if we did cull the rare cancers, it went up to just under 94%. And these are the same for the lines for histology. And you can see when the culling doesn't have much of an effect on histology, it's around 95%. So 94–95% of the time, our system finds the right answer, which is really good. Now, here's an example. This is one of the unseen reports. This is from the sequestered test data set. We have the truth from the cancer registry. So both the cancer registry and our system both said the site was lung. And you can see there, it says highlighted in blue, lung involving the left lower lobe. And notice that they aren't beside each other, but it can still, our Cabernet can still figure that out. But when it comes to histology, there was some discrepancy. The cancer registry said it was spindle cell carcinoma. And if you read through the report, you see things like this. Focally, a couple of small proliferations of bland spindle cells. The mass in the lower lobe is composed of spindle cells. So it was reasonable that the cancer registry would say this is a spindle cell carcinoma, but there's a subtlety to it. Up here, there's this phrase that says surgical path comment. And what that means is they did a stat pathology analysis during the operation. And the surgeon wanted to know what it was. They called for a stat analysis. They went off and did it, came back, gave the surgeon the answer that he or she wanted. The surgery went on, and then at the end, the full excised tissue went back to the path lab where they did further analysis, and they had the option to change their diagnosis. And in fact, that's what happened in this case. So you can see at the bottom here, it says, there's a bunch of stuff that I cut out because this was a couple pages long, but it says the differential diagnosis includes sarcomatoid carcinoma and inflammatory myofibroblastic tumor. And they ended up in the end saying final diagnosis is sarcomatoid carcinoma. So they changed their diagnosis between the stat analysis during the surgery and the final diagnosis afterwards. And that happens a fair amount of time. So the cancer registry is by algorithm obligated to report the very first conclusion, the very first diagnosis, even if it's not the final diagnosis. So what they did is right. But our algorithm is trying to find the final diagnosis, and that's why the discrepancy. But still, our BERT came back and said, this is pseudosarcomatous carcinoma. And I Googled that, looked for it, did a text search for it in this pathology report, and that phrase does not exist anywhere in this report. So how in the heck did it find this? Because remember, it's trying to find passages of text that exist in the report is the answer to that question. So how did it come up with this if it didn't exist in the report? So I pulled out the purple book and looked it up, and lo and behold, sarcomatoid carcinoma is a pseudonym for pseudosarcomatous carcinoma. So not only did it found sarcomatoid carcinoma, it mapped that onto the correct phrase and the correct code. It learned how to do that through the training. So that's really cool. I thought, well, this is pretty neat. So and here's an example.
Hi, so this is a program I've written to demonstrate Cabernet in action, and I'm going to go over the major parts of the display here. So at the top, the title, Pathology Report Extraction Review. This block of text is the pathology report, and you can scroll through it, and you can see that it's quite long. It's very complex, a lot of information in there. Up at the top, I've added a tool which actually screens the pathology report to determine if there's a malignancy, and you can see here that it's determined that this report does contain a positive, at least one positive indication. This report also happens to be part of our sequestered test data set, so we do have the ground truth available from the cancer registry, and that's listed here. And you can see the site is endometrium and the histology is adenocarcinoma endometrioid. Down here are the answers to various pre-specified questions, including what's the tumor site and what is the tumor histology. And you can see if I click on these pull-down menus, it's showing the top 5 results, but in this particular case, it's basically essentially 100% certain that the site is endometrium, and that happens to agree with the cancer registry. And in terms of histology, again, it's pretty much, you can click on this to see the top 5 answers, but it's basically 100% certain that this is endometrioid adenocarcinoma, and that happens to agree with the cancer registry. Now, I've also started to extend the system by asking it to answer pre-defined questions related to tumor size, stage, grade. And you can see that these are the answers to the various questions are outlined in color in the text. So site and histology are outlined in this sign color. So you can see histology here, adenocarcinoma endometrioid. If you scroll down, there's endometrium as the site. These new questions are, the answers are outlined in yellow. So FIGO grade 1 is the grade. This is the size that it's determined. You can see it says tumor measures such and such a size. And the tumor stage has got to be in here somewhere. There it is. Primary tumor PT, PT1B is the stage. What's cool about this is you aren't just restricted to predefined questions. I've added a field over here where you can type in a question and ask it to go find the answer. So let's, here's something. The carcinoma involves more than 50% of the myometrium. So let's see if it can find that. So we know the answer to this. How much of the myometry is involved? hit return, and then click on answer, and it'll go look for it. And it says more than 50% over here. And it highlights it in red in the text and labels it as the answer, more than 50%. So there, it found that. That's good. There's type in some other things here. Let's see. Something a little more useful. How many pelvic lymph nodes were examined? Question mark. Hit return. It processes and codes the question. Click on answer, and it goes and looks for the answer, and it comes back with the answer of 21. Should be highlighted in red. There it is. Total number of pelvic nodes examined, sentinel and non-sentinel, 21. So that's pretty cool. It found that.
And you can just ask all kinds of questions. And eventually you'd want to put a voice interface in front of this. You just ask. And you could ask it to, for example, go and find patients that have this characteristic, and it would go get them for you. So the way that we had implemented this about around the time I left Moffitt is I had set up a system, a batch job. Essentially, you dump a bunch of path reports into a folder, and it would run and process each of them and produce as output the top 5 predictions for site and histology, and also was starting to produce predictions for grade and stage and things like that. But to train it to do other things is pretty straightforward. So the last thing I'm going to talk about is medical imaging. And this is work that I actually started at Mayo and carried over to Moffitt. So we were interested in segmenting brain tumors. Lots of people in the world are segmenting brain tumors. There's probably 1,000 publications a year on new ways to segment brain tumors using deep nets. But the vast majority of those papers work on public domain data sets. They're done by folks in engineering and computer science departments that aren't part of an academic medical center. So they don't have access to images. So you understand they go and get the data that they have access to on the web. What we did is we actually used real clinical data. And this is what real clinical data looks like. In a clinical trial, if the image is kind of messy, they rescan the patient until the image is pristine. So the system I built runs in the cloud on Amazon, takes about 1.5 minutes, and it takes as input a T1 post contrast and flare, produces a bunch of volumes as output. And this is an example of, in the sequestered test data set, the worst agreement between the technologists and the deep net. So the ground truth is a voting system from multiple technicians who have segmented. At least 2 technicians segmented each tumor, and we use that as the ground truth. So just a quick show of hands, which do you think is better? How many people think that A is better? A better representation of the disease. How many people think B is better? So A is better. It's a better representation, and it was actually done by the deep net. And this is another example of poor agreement. And I'll just jump to it. The one on the top, which is the better segmentation, was done by the deep net. And I saw this quite a bit. There are cases in the opposite where the human was clearly better. It was kind of strange that there were a fair number of cases where the deep net was better. So I built another system that runs in the cloud on Amazon to allow radiologists to do remote side-by-side comparison of deep net and human labeled lesions. And so these are the same lesion, one segmented by humans and one segmented by the deep net. And I had 20 neuroradiologists, board certified, go through and score them side by side, and they put a score in that panel at the bottom. And when all was said and done, we could calculate and do some statistics on their scoring. And the red is how they scored the deep net, and the blue is how they scored the technicians. And on average, they scored, the deep net had a higher quality of segmentation than the technicians. Okay, we've seen that before, but the catch here is that these are the same technicians that created the training data, right? It's not an independent set of technicians. These technicians created the training data, and they also created the labels for the test data. So if they created the training data, how could the neural net learn to do better than its teachers? It goes against common sense. You see things like this all the time. This is for a white paper by a data labeling company. Why your AI model is only as good as its training data. And I'm here to tell you that that's just wrong. Often your AI model is better than your training data. And I'll try and run through this quickly. Why? Well, this is something I'm working on right now. Hope to publish. This is a pathology data set, colon, adenocarcinomas, and benign, 5,000 of each. We split it into train and test subsets, completely sequestered test subsets, and all the labels here are perfect. And so what I did is I replicated this data set and intentionally mislabeled the training labels. So I labeled some malignant as benign and vice versa. And then I trained a model from scratch using random initialization. And so this shows you the result. You can see the accuracy of the training labels on the horizontal axis and the accuracy of the model applied to the sequestered test data set with perfect labels, okay? And the accuracy goes up. The red line is if they were equal. So for example, if you have 80% accurate training labels, 1 in every 5 labels is wrong, the model still learns to get 95% accuracy on the sequestered test data set. Why? Well, briefly, this is why. This shows the actual distribution of predictions for accuracy, label accuracy, the training label accuracy varying from 50% top left to 100% bottom right. And when you're doing a classification, a binary classification task, you can say anything above 50% we're going to call positive, anything below we're going to call negative. So here, anything above 50% is the vertical red line is a correct classification. So when the training labels are 50% accurate, they're just random, it gets about 50% accuracy in the model when it's trained. You might expect that. But notice as you increase the accuracy of the training labels, that histogram starts to shift. In fact, the peak of the histogram hovers around the level of accuracy of your training labels. But as it moves to the right, as your quality of your training labels improves, it drags a lot of the answers across that red line. And that's why the accuracy is higher than the accuracy of the training labels. So you get up to 80%, which is bottom left. You can see it's a highly skewed distribution, and the vast majority of the answers are above that red line. That's how it can get 95% accurate. So it's just a simple statistical process that your model can learn to see through errors in the training labels. So don't believe it when they say your accuracy is only as good as the data you train with. These things can learn to see through that. So the last thing, just to summarize, what I plan to do here in Alberta is, deploy those things that I've done before here, but also to build a team. And I'm really, the way you do this properly, in my experience, is you work very closely with the clinicians and the frontline workers, the nurses and the staff, and it's an iterative process. You break things, you fix them, you learn from your errors, you come back with a new model in 2 weeks, and you try that out for a while, and you help build trust and confidence with the clinical team by doing it that way. And when you finally converge on something that's useful, you don't just deploy it right away. You do that silent period where you run it on new prospective unseen data to make sure that it really works. And this process, you learn a lot, but you also get buy-in by the clinicians because they're part of the development team. They're giving you feedback on what they want. Sometimes what you build is not what you intended to at the beginning, right? Like in the case of that sepsis tool, what ended up being most useful to them was not a model, but the ability to look at the data. And we wouldn't have found that if we'd been doing a throw it over the fence type of approach. So that's it. Ran a little over. Happy to take questions. Yeah, no problem.
Okay, so same protocol as we've had all day. If you've got any questions, you're welcome to come on up, start forming a line. Until then, I will field some questions that we've got from the chat. So the first question I have is, how accurate are the ICD codes assigned by the billing department?
We don't know, but they're probably, they have they get paid based on those codes. Just let me say that. So there's vested interest in a lot of people to make sure they're right, but I have no idea how accurate they are. They're probably pretty good.
Fair enough. Next question. Is memorizing some training examples an issue for Cancer BERT / how do you protect the privacy of over 250,000 pathology reports patients?
Yeah, so absolutely. So one of the issues with transformers is issue or benefit is the bigger they are, the more parameters in the model, the better they perform. And it's not a linear improvement, but as they get bigger, they do better on multiple tasks. So ever since BERT was published, there's been essentially an arms race to build the biggest transformer model. And I think currently we're up over 175 trillion parameters. And by parameter, it's a weight, or you can think of it as a weight in logistic regression model. If you're familiar with biostats, these are a lot more complex models. But the BERT that I was working with had 110 million parameters. So that's orders of magnitude fewer. And the problem with the big transformers benefit is one of the things they do is memorize their training data. So if you were to train that on patient data and then release the model, people could ask it questions and probe it and pull out protected health information. And that's been shown to occur on some of the big models. So it's an unknown question right now. But my personal belief is at 110 million parameters, it's not memorizing the training data. It's actually learning to find patterns. At 175 trillion parameters, it almost certainly is memorizing training data, and where the threshold is, I don't know. So that's definitely an issue, unresolved.
Our next question is, can you explain the clinical significance of segmenting brain tumors? Why is it important?
Yeah, sure. So segmenting brain tumors is important for a bunch of things. This can be input into radiotherapy treatment planning systems as a target, where you want to put the 95% dose interval. It's important for surgeons when they're preparing surgery. They have a target volume that they'd like to remove. And those are the two main clinical applications for debulking the tumor, either through radiotherapy or surgery. You want to know the border of it.
Hello, I just wanted to ask, so earlier you mentioned that novel technologies like these in the medical field take quite a while to become accepted. So with promising results like these, do you think, how long do you think this might take to be applied in the medical field officially?
So how long will it take? It depends. So my philosophy is that we build tools, we're building power tools to handle complexity. That's what we're doing. So there's been a lot of talk about, even today, AI replacing physicians. Hogwash, you forget about it. It's like the old problem worrying about overpopulation on Mars. Well, maybe someday it'll happen, but I'm not worrying about it in my lifetime. And I'm not worrying about AI replacing physicians in my lifetime, not even radiologists and people who look at images. Because if I train an algorithm to go determine whether a patient has pneumonia in the lung, and it's looking at a chest CT, what about incidental findings? What if there's something in the gallbladder? It doesn't know to look at the gallbladder. It hasn't been trained for that, but a radiologist does, right? They'll go, oh, there's something. That's how a lot of stuff is found. So even in visual applications of medicine, these things are power tools to help physicians do their job faster and more efficiently and more enjoyably. Like the two, artificial intelligence, I often say it's certainly artificial, it's not so intelligent, but what it is good at is pattern matching and pattern finding and cranking through tons of data. And people aren't good at that. We find it rote and boring. So let the computer do that and let the clinician focus on what they're good at and what they enjoy, and put the two together to work better together. This all this stuff about replacing radiologists is just that's said by people who've never actually been in a radiology department and see how they work. Not going to happen.
Thank you.
So for pathology reports, of all the different types of reports in medicine, those are one of the more standardized types of reports. Can you see the same method being applied to more or less standardized reports, like patient charts, where there's almost no consensus on how to document?
Yeah, so the question was, the pathology reports are pretty standardized. In some places, and how would you apply this to less standardized reporting? At Moffat, they don't use structured reporting. So these pathology reports are not standardized at all. Let me tell you, they are all over the place. And these are solid tumors only. I didn't say that. I should have said that. But for the hem-onc cases where it's blood cancer, that the head of that group was a real believer in structured reporting. And she basically imposed on all her pathologists that they would use structured reporting. So at Moffat, the hem-onc reports are pretty good. They're pretty structured. But the solid tumors, the path reports are all over the place. It's just crazy. So this, I think, would translate pretty well to unstructured clinical notes and should also translate to radiology notes and any kind of note that you might come across with tuning. So you could take this as a base model and then tune it.
Okay, we've got time for one more. The next question reads, you showed us some examples of when the student was better than the teacher. Do you think this is domain specific or dependent on how much of an expert the teacher is?
Yeah, so that's a great question. The answer is unknown. So it comes down to, the way I like to think about it is, when we are labeling data, we almost always have a fixed budget for labeling. It could be fixed time, fixed money if you're hiring people to do it. It may be the trouble and the difficulty of getting experts in one place to reach consensus. So we almost always have a fixed budget of some sort. So let's assume we have a fixed budget to invest in labeling our training data. The question now becomes, how should we use that budget? Should we try and use all of our resources to get a small number of the highest quality labels that we can? Or would it be better to accept some errors in the label, but get a larger volume of them? And I think that will be case by case dependent, but at least it opens up the option now. Up until this point, especially when it comes to medical image segmentation, the belief was we must have the best answer that we can get. And in a case like a brain tumor, what is the truth? You don't know where that tumor ends because it's cellularly infiltrative throughout parts of the brain. And even if you looked at it under a microscope, you'd have a hard time saying where the tumor stopped and normal tissue began. And certainly at the radiological level, when you back out and you're at the spatial resolution of millimeters, neuroradiologists disagree. Even if they've got 20 years of experience, you ask them to put a border down and they'll disagree with each other. So there is no gold standard truth. We can maybe get silver or bronze standard, but can we back that off and just get trained technicians? I wonder if somebody who's just crowdsourced, who's never really seen a brain tumor before, could segment these and we could learn something from that. So it's an area to be investigated, but it's likely domain specific.
That brings us to the end of our Q&A period. Thank you very much, Dr. Mitchell.